Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4, that is Hydro and Renewable Energy Power Generation Systems. In our last lecture, we discussed about Hydro Power System Part 1, in which we have given emphasis on water power and specifically power generation through Pelton wheel. So, moving further in the second part of the lectures, we will introduce some more topics, mainly this degree of reactions. Then also we will introduce another class of turbine, which is known as Francis turbines. Then we have some basic introductions for propeller and Kaplan turbines. Then for comparison of turbines across various applications, we are going to define the specific speeds for all types of hydraulic turbines. And finally, when these turbines are being used as a prototype in a realistic hydropower systems, there is also a need that similar type of turbine has to be tested in the laboratory, and such to do that we need to maintain the model size, designs, and for that reasons we are going to define certain parameters like scale ratio, unit speed, unit power and unit discharge. So, this is the overall philosophy for our lecture. Just to give the brief insight, in our last class we have emphasized water power is a renewable form of energies, but only criticality of this power generation is that we need to have a potential height. Another positive side of water is that water has a density of 1000 kg per meter cube, and if you are a large slug of mass is available at certain height, then electric generation, electric productions will be a huge number if the turbine is supposed to run throughout the year. So, this is the very basic theme of hydroelectric power plant. Although the initial infrastructure is very high, but the running cost is low and we do not require high skilled manpowers. Anyway, in our last lectures we have emphasized a class of turbine which was categorically told as impulse turbines. It is a Pelton wheel, and Pelton wheel is a very basic old concept, was known as a water wheel. People used to harness water power through this wheel. But one important thing in this Pelton wheel, that is that starting from the height of where the water is available to this turbine point, that is where the wheel is positioned, then the entire flow passage is almost atmospheric. So, we have to first convert the potential head to kinetic head and energy, and that kinetic energy was through these nozzles. That was the essentially arrangement in a Pelton wheel, and nozzle jets, nozzle gives the water jets, that in turn rotates the wheel. So, this is the basic aspect, that why we call this as a impulse turbines. Now, let us try to understand this theoretical background of this. Now, if you look at this Bernoulli's equations at any inlet and outlet of the turbines, then we can write that equation P 1 by rho g plus V 1 square by 2 g is equal to E plus P 2 by rho g plus V 2 square by 2 g. So, here E is nothing but the energy transfer from fluid to water. This is nothing but your potential head. So, now if you assume the P1 and P2 to be atmospheric, so this energy available will be like V1 square minus V2 square by 2g. So, this is nothing but your velocity head, and this is exactly what we do in a impulse turbines or in a Pelton wheel. So, entire water always experiences atmospheric pressure throughout its path, or the entire velocity head is being converted to for power generations, or that is energy transfer from fluid to rotor. Now, another category of turbines that can be thought of is that, now let us say instead of making P1 is equal to P2, let us say we will make V1 is equal to V2. So, in that case your velocity head will vanish. Now, what we will arrive at is E, that is energy transfer from fluid to rotor, is P1 minus P2 by rho g. So, this is nothing but your pressure head. So, ideally this is called as a pure reaction turbines, but however, in our basic structure of turbine manufacturing, we cannot have a pure reactions, although we can have complete impulse turbine as you see in the Pelton wheel, but reaction turbine is not possible. So, there has to be some compromise between velocity head as well as the pressure head, and such turbines we call as a mixed flow turbines. So, they can be neither considered as, because both velocity head and pressure head take part in the energy transferring from fluid to rotor. Now, basically this, considering this aspect, we define a term which is called as a degree of reactions for a hydraulic turbine, which is defined as the ratio of energy transfer due to pressure drop to the total energy transfers. And considering this, we call either a pure impulse or pure reactions. So, if you take pure impulse, it is a Pelton wheel, and for this Pelton wheel we can say its degree of reaction is 0. Now, when you say pure reaction, we get the energy transferred or from the fluid to rotor, in which the energy due to by virtue of the pressure drop exerts a reactions by the Newton's third law of motions, and such a turbine we call this as a reaction turbine. So, here if you see this particular diagram, this is for a Pelton wheel. We can see that there is a nozzle. That nozzle essentially gives the necessary water jet for running the bucket of water. So, that means velocity is getting converted to energy transfer from to the rotor. Now, considering this, since we say that we cannot have complete pure reaction turbines, so we define this degree of reactions. Now, considering to be more precise about a degree of, to calculate the degree of reactions, what we define is that from Euler equations we can actually calculate, which we derived in the last class, that is energy transfer from fluid to rotor, like is equal to 1 by g into Vb1 Vw1 minus Vb2 into Vw2. So, this refers to this particular diagrams. B1 stands for either you can say bucket velocity or blade velocity. For a Pelton wheel, V1 and Vb2 are equal, but since we are looking for a reaction turbines, we will say that there will be both the term V1 and V2. Now, if you take the these particular expressions, you will see that there is a term Vw2 and Vb2. This quantity is typically negative. So, if you somehow make this quantity to be 0, that means if you by designing a suitable blade, if you can make Vw2 component to be 0, then we can maximize this energy. So, Euler's equations now becomes, we can rewrite it as Vb1 Vw1 by g. Now, this is the maximum energy which can be transferred from fluid to rotor, but degree of reactions, that means the component of energy due to pressure drop is nothing but P1 minus P2 by rho g, and this can be, since by Bernoulli's equations, this can be rewritten as E minus whole bracket V1 square minus V2 square by 2g. So, these equations can be simplified by to find these expressions for degree of reaction which is in terms of absolute velocity V1, V2, VB1 and VW1. So, this expression is normally used if it is a mixed flow type of turbines or it is a reaction turbines. So, we have told that there is no pure reaction turbines. So, there has to be some component in which the energy is transferred both due to both pressure head as well as the velocity head. Now, the most versatile turbines under a reaction turbine, we call this as a Francis turbines. So, here we can say that the energy transfer from water to runner takes place due to the static pressure drop as well as the velocity head, and they are mostly preferred for medium head and medium discharge. And since it is a reaction, not a pure reaction turbines, so it is categorically told as a mixed flow variety of radial entry and axial outlet. Now, how it is radial entry and axial outlet, you can understand from this figure. So, water from the penstocks enters to the scroll, that means water entry is from this side. So, this is the from penstock. So, penstock is nothing but the water pipe or conduct in which the high head water is allowed from certain locations to the location of the turbines. So, when it enters from the penstock to this, so it passes through a casing which is called as scroll casing, and this scroll casing surrounds this runner, and this runner is integrated with two types of blades. One is vanes, one is called guide vane, other is called runner blade. So, complete water gets interacted with this all the guide vanes. So, slug of water that enters to the penstock, it is completely interacts with the all types of guide vanes. The role of the guide vane is to allow the suitable passage for the water to its corresponding blades, which is called as runner blade. So, this is nothing but to give the suitable velocity positions and velocity triangles for maximizing energy of water. So, this is what we call as runner blades. Now, when it is discharged vertically to this plane. So, you can see water that comes from the guide vane to this, it is comes through in this top view. You can say how water is allowed to get discharged after this runner blade, and it passes through in a controlled way in a tube, what is called as a draft tube. So, normally since we say that it is a controlled, the Francis turbine is controlled through the pressure difference because it is a reaction turbine. So, that is the reasons in order to have a smooth passage of water from maximize the energy available from the water, it has to pass in a controlled way through this draft tube to the tail race. Tail race is nothing but a discharge point of water. So, this is the overall picture. What we can say that if you look at the runner, they have cork blades, normally it is 12 to 22, and they are welded with the shroud, which means that these runner blades are fixed blades and they cannot be deflected, or they cannot be, for a given turbine, they cannot be disturbed. So, there are 12 to 22 number of cork blades. Then another important point that I have already mentioned is that in a Pelton wheel, we say that complete passage of water is purely atmospheric, but when the water jet comes, that water jet hits at a particular time to fixed number of buckets. Not entire buckets of Pelton wheel is exposed to the water jet. So, sequentially one by one buckets gets exposed to this water jet. But in a Francis turbine, what you see that complete water gets, means all the guide vanes of this runner, they are exposed with the complete slug of water, and we say that it is a pressure regulated device, and that is the reason, and entire things happens in a closed tube, and before it is getting discharged to the tailless. So, this is the basic difference between the Pelton wheel and the Francis turbines. Now, the free end of the draft tube, which is the discharge passage of the water, is submerged deep into the tailless, so that the water does not see any kind of atmospheric pressure in its path. Now, let us try to understand the how energy is harnessed from the water by looking at the velocity triangles that is drawn for a Francis turbine. So, what we seen is a particular one particular runner blade, and we have drawn these velocity diagrams. What we have is V1 stands for absolute velocity of water that enters that gets discharged from the guide vanes. So, this point is V1 is comes from the guide vane, and this is your runner blade. Now, when runner is also rotating, so when the water gets discharged, we see its relative velocity, the VR2, it is getting discharged. The first point is that there are angles, we call this as a guide vane angles alpha 1 and runner blade angles beta 1, and then if you look at this particular velocity triangles, we have two components Vf1 and Vw1. This Vw1 consists of entire length. So, it is basically Vw1 is directed opposite to this, so that we get this velocity V1 in these directions. So, this is Vf1. So, what we see is this inlet velocity triangles. Now, the angles are so designed, we need to ensure that your Vw2 should be 0, so to harness maximum energy. So, when Vw2 is 0, then essentially we have this expressions Vf1 is equal to Vf2. What is this Vf1? Vf1 and Vf2 is nothing but for this Francis turbine we call this as a flow velocity or meridional velocities, and that is Vf1 is equal to Vf2, and that is nothing but your V2. Another important point is that we need to have Vb1, and there are two velocity Vb1 that is inlet and Vb2 at the outlet. And here this alpha 1, beta 1 and alpha 2 is 90. So, here we say alpha 2 is equal to 90 degree. So, this through this process we get these two expressions. Sorry, alpha 2 is 0 degree. So, axial discharge, there is no wheel component, and beta 1 is inlet blade angle, alpha 1 is exit blade angle of the guide vanes. So, through this process we can find out the expressions for work done per second per unit mass, which is E is equal to Vb1 and Vw1, and looking at this velocity triangles, this E can be expressed in terms of Vf1 and with the angles alpha 1 and beta 1, and we also can find out Vw1, Vb1 from this velocity diagrams. Ultimately, at the end of things, our main analysis is to find out degree of reactions, blading or diagram efficiency and hydraulic efficiency. These are the three efficiency we are interested. First is what is the blade or diagram efficiency? That is nothing but E, which is the work done per second per unit mass, divided by E minus E1. What is E1? E1 is nothing but your loss of kinetic energy. And that loss of kinetic energy, since blade is rotating, and there is a difference in the velocity, relative velocity of water, that is VR2 and VR1. This loss is accounted in terms of loss in kinetic energy. Now, from these expressions also we can find the degree of reactions expressions, we can find the hydraulic efficiency, that is nothing but E by H. So, H is the height or net head available for the turbines, then we have this overall efficiency. So, these are the some mathematical expressions that can be laid down for a Francis turbine. Then we will move to next segment of turbines, which is propeller or Kaplan turbines. So, the propeller and turbines are generally axial flow device. So, they are preferred for axial flow, and main intention is that they provide large flow area by utilizing larger volume of water with small velocities. So, possible way of increasing possible way of power harnessing power is through two ways. One is increase head, high head low discharge, or low head high discharge. So, here we have larger volume of water, but small discharge. So, there are some locations where large quantity of water is available, but no let head is less. So, such cases we use propeller turbines, and actually these propeller turbines, they have axial flow runner with 4 to 6 blades of airfoil shapes, and moreover there is a difference in these blades of propeller turbines with axial flow. In the Francis turbines, the blades are fixed, but here we have adjustable blades. The propeller turbines are reaction turbines which are preferred for low heads, that is in the range of 4 meter to 80 meter, but higher specific speeds. A special class of turbines in the propeller turbine category is the Kaplan turbines. So, in the Kaplan turbine is a turbines, they have a advantage that the design features or manufacturing features of Kaplan turbines is that the turbine runner blades can be adjusted depending on the load requirement. For example, load changes. For example, at the downside of this electric power generations through this rotation from this turbine, when there is a change in the load, electric load in the grids, then it automatically affects the locations at which power is generated, and it is nothing but at the location of the turbine. Now, for that, if there is change in load, we need to adjust the power. For adjusting the power, we have to look into the adjustment of flow rate. For that flow rate adjustment, that is mainly relied on the adjustment of guide vanes. So, for this Kaplan turbines, there are possible advantage of adjustable runner blades in which can cater the load changes at the time of need. And why we say this? Because efficiency of a reaction turbine depends on the inlet blade angles. Since the Kaplan turbines allow the variation of inlet blade angles with change in the load, the turbines can run at maximum efficiency at all loads, and their hydraulic efficiency is about 90%, and their specific speed varies from 260 to 280. So, these are the some velocity triangle features for a propeller and Kaplan turbines. Here we can see that the exit vane angles alpha 1 here varies from 45 to 70 degree, inlet blade angle beta 1 varies from 20 to 60 degree. So, these are the some numbers, but if you see the outlet triangles, here V2 is no longer VF2. So, here we have a VF1, also we have a VF2, and these two numbers are not equal, and of course, we have V2 as well, that is absolute velocity of the jet, then relative velocity. Another significant feature is that since the design of the blade, that means it is at the hub and it is at the tip. So, there are two locations, that is at the hub and at the tip. So, at these two locations we can have the change is very gradual from the hub to tip, and every locations we can have velocity triangles. So, this allows the change in the power by adjusting the blades, but we are not going to deep into those aspects, because we will have a series of velocity triangles at different locations of this blade, that is from tip to hub. The next segment of the topic of our discussion is the specific speeds. Now, we know all types of turbines, mainly Pelton wheel, Francis turbines, propeller and Kaplan turbines, and we know their working conditions, velocity triangles. But when these turbines are supposed to be used, their models has to be tested effectively. Now, for the testing the model, we may not have facility for generating a very high head, and also we do not have a facility for generating for large powers. So, for that reasons, normally what has been done is that a analogous parameter is defined, and that analogous parameter is remains same for the model as well as prototypes. So, here we use the concept of dynamic similarity or similarity rules, based on which the models and prototypes can be compared. Now, one such parameter in this case is the specific speed. Now, to define the specific speed, we know that there are three important parameters is desired for power generations. One is head of water, second is rotational speed, then third is how much power is we are going to generate. So, these three things has to be considered together to define this specific speed, and that has to remain same for the model as well as the prototype. So, by considering this, the specific speed of a turbine is defined as the speed of operations of a geometrically similar model turbine which produces 1 kilowatt power while operating a head of 1 meter. There are two things here you need to focus. First thing is that it can be a non-dimensional number or dimensional numbers, and through this process or through variety of consideration of similarity rule, the specific speed of a turbine is defined in a dimensional form, that is n into square root of p divided by h to the power 5 by 4. Now, analogous term to this is a non-dimensional form. To make it unitless, we multiply rho to the power half into g h to the power 5 by 4. So, this is another way of expressions, but however, at the end of the day and end of our analysis, we are it is just a matter of scaling, but we will mostly prefer for these expressions, that is specific speed defined by n s is equal to n square root of p divided by h by to the power 5 by 4, and we will not intentionally will not write in the units. So, we will just say the specific speeds for all types of hydraulic turbines that vary from 4 to 1100. So, main significance of this specific speed is that lower specific speeds denote slow runner, high specific speeds imply fast runners. So, in our last lectures I have given these slides that this particular table which talks about class of turbines depending on the flow directions, class of turbines based on specific speeds. Now, we have more focused considering for all types of turbines, and they are fall in three categories: low, medium and high, and all turbines also can be useful in these three categories, and based on their specific natures they can be operated at for maximum and minimum power and maximum diameters and suitability of a particular locations. Another significant features of considering model and prototype is the scale ratio. Scale ratio, unit speed, unit power and unit discharge, and it is mainly related with respect to model and prototype. But previously we have defined some terms like speed ratio, which is the ratio of blade velocity to water velocity, and for different types of turbines, Pelton wheel it is 0.4 to 0.47, Francis is 0.5 to 1 and propeller is 1.5 to 3, and also with respect to Pelton wheels specifically a jet ratio is defined and which is typically maintained 10 to 24, but these parameters are specific to respective turbine. Now, if this prototype turbine has to be tested with respect to model, then we define this term which is called as a scale ratio. So, the scale ratio represents the ratio of diameter of the model turbine to its prototype. But when you make this comparison, we must say they should have same specific speed. Now, looking at the comparison between these two, what is the most common? One is BB blade velocity. If you recall, this blade velocity or bucket velocity is pi dn by 60 and speed of water square root of 2 gs. These two expressions says that BB is proportional to dn and V is proportional to square root of h. So, that way, looking at the similarity rule, we can write dn is proportional to the square root of h. So, considering this, we can find the expressions of the ratio which is called as a scale ratio, that is diameter of the model to the diameter of prototype, that falls that is a proportional to this speed range for the prototype and the model as well as square root of h of model and the prototype. Now, moving further, same logic we apply for to define the unit terms. They are nothing but the operational characteristics of hydraulic turbines. The unit speed is defined as the speed of a geometrically similar working turbine which works on the end of 1 meter. Unit power is the power generated by geometrically similar turbines working under 1 meter. Unit discharge is the flow rate of the turbine working under the head of 1 meter. So, first thing from same logic we find when you say BB proportional to B, we say N is proportional to square root of H, and when H is equal to 1, so K1 becomes N, and that term we call it as a unit speed Nu. So, Nu is equal to N by square root of H. With same logic, when you define the power, P is equal to rho Q G into H, replacing flow rate into A into V, we arrive at P is proportional to the H to the power 3 by 2. So, P becomes K2 into H to the power 3 by 2. When H is equal to 1 meter, we define unit power Pu is equal to P divided by H to the power 3 by 2. And in similar way, we can find the unit discharge Qu is equal to Q to by H to the power half. So, these parameters are mainly required when you discuss about the model as well as the prototypes. So, the whatever we have discussed so far, the complete comparison of the turbines based on these specific parameters, Pelton wheel, Francis, propeller and Kaplan turbines are presented here. So, this is, you can say, is the summary sheet of the all types of hydraulic turbines, their respective efficiency, specific speed, power generation capability, head and RPM. So, with this we complete this hydraulic component of hydroelectric power systems. So, before you conclude these lectures, let us try to solve some numerical problems based on our discussion in this lecture. So, the first problem is about the Francis turbines. We discussed this Francis turbine, and here we present this velocity triangles. We have this is inlet and this is outlet velocity triangle. These velocity triangles are useful to find the energy which is getting transferred from fluid to rotor. So, two important things for this Francis turbines, we have this VW1 component and VF1 component that constitutes the velocity vector of V1. Correspondingly, this VW1 is associated with VB1, which is there in the inlet triangles. Then we have blade angles and guide vane angles. Then we have the outlet triangles, we have similar terms beta 2 and alpha 2, and here essential feature is that Vf1 and Vf2, that is flow velocity, remains same from inlet to outlet. Now, with this summary, what we are going to solve these problems. So, datas are given, it has the inner diameter 0.75 and outer diameter 1.5 meters. So, these two diameters will decide Vb1 and the Vb2. We will see how you need to find out. There is a head 150 meter, specific speed 120, but what we do not know is the speed or RPM. So, for to get this RPM, let us take this specific speed expression, n is equal to ns is equal to n square root of p by h to the power 5 by 4. Now, while using these expressions, one must ensure the power should be in kilowatt. So, here it is producing 15 megawatt. So, you have to make it kilowatt, that is 15,000 kilowatt, and h should be in meter, and here h is equal to 150 meter. Now, inserting this number and that specific speed here is 120. So, inserting this number, we can get n is equal to 150 to the power 1.25 into 120 divided by square root of 15,000. So, this number is 514 RPM. So, once we have this 514 RPM, we have Vb1 is nothing but pi d n by 60. So, dB1 d1. So, here d1 is 1.5 meter and n is 514. So, this will give you Vb1 as 40.4 meter per second. Now, we can write hydraulic efficiency eta h is equal to Vw1 Vb1 divided by G times h, that is equal to 0.9, and then we have Vb1, we have h is equal to 150. So, this will give you Vw1 value. So, Vw1 will be 0.9 into 9.81 into 150 divided by 40.4. So, this is 32.8 meter per second. Now, looking at the inlet triangle, we can write tan alpha 1 is equal to Vf1 by Vw1. So, Vw1 is known, Vf1 is not known. So, alpha 1 is 10 degree. So, this will give you Vf1 is equal to 5.8 meter per seconds. Since Vf1 is equal to Vf2, so you can say Vf2 also 5.8 meter per second. Another expression we can write, which is tan beta 1 Vf1 by minus Vw1 plus Vb1, because it is negative. Vw1 is in opposite direction of Vb1. So, considering this, we say 5.8 divided by 40.4 minus 32.8. So, this is 0.763. So, this will give you beta 1 as 37 degree. So, we have inlet and outlet blade angles. So, we have first beta 1 is 37 degree, it is inlet blade angle. Now, for outlet blade angles, we know what is V by 2, Vb, we have to say Vb by 2, and it is exactly half of this. So, we can say Vb2 is Vb1 by 2, because d2 is equal to d1 by 2. So, Vb2 now becomes 20.2 meter per second. So, from the outlet blade triangle we can say tan beta 2 is equal to Bf2 by Bb2 minus Bw2. So, this will give you tan beta 2 is equal to 0.287 or beta 2 is equal to 16 degree. So, we have inlet blade angle is this and we have outlet blade angle is 16 degree. Okay. So, this is the first problems, and in the second problem this is based on the specific speeds. So, we have a model and we have prototype. So, the parameter associated for model we write power Pm, Pp, head Hm, Hp, diameter Dm, Dp, speed Nm, Np. Okay. Now, you will use this word. So, first thing is that we have given with the turbine specific what remains same for both is Ns. Specific speed is same for both of them. So, solution from the problem we can start with the first thing, that is for model. So, we are asked about the speed, power and scale ratio for the model. So, we will do it first for the model. So, power developed by the model we write rho Qm G, also we have Qm and Qp flow discharge, Hm into efficiency, and efficiency is 90% and Hm model has to operate at a head 4.5 meter, Qm is 0.6 meter cube per second, rho stands as 1000 kg per meter cube, G stands as 9.8 meters 0.8 meter per second square, 9.81 meter per second square. So, from these things, and this power has to be in kilowatt. So, you have to multiply into 10 to the power minus 3 kilowatt. So, by inserting these numbers we can find out power developed by the model is 23.83 kilowatt. First answer we get what is the power developed by the model. Then what remains same? Specific speed. Then we need to find out speed of the model. So, we recall specific speed Ns is equal to Nm into square root of P divided by Hm to the power 5 by 4. So, Hm is known, and that number is 200. So, this will give you Nm is equal to 200 into Hm. Hm is 4.5 to the power 1.25, that is 5 by 4 is equal to 1.25. Square root of P is Pm. So, that is 23.83. So, speed of the model is 268.4 rpm. So, this is the second answer. Third answer, scale ratio. So, scale ratio you have to say that is dP by dm is equal to Nm by Np square root of Hm by Hp. But what we do not know is for prototype. Now, for the prototype we have PP is equal to 30 megawatt or 30,000 kilowatt, NP is equal to 200 RPM. So, we need, and we can say NS is equal to NP into square root of PP divided by HP to the power 5 by 4, and that number is 200. And what is not known is this will give you HP is equal to 61.8 meter, because PP is known, NP is known, we do not know HP. So, HP is 61.8 meter. Now, from this expression we can calculate dP by dm, that is scale ratio. Nm is 268.4 divided by Np is 200 into 61 point model height, model HM is 4.5. HP, sorry, this is HP and HM. So, it is 61.8 divided by HM is 4.5 to the power half. So, dP by dm is equal to now approximately 5, or dm is 1/5 of dP. So, this is the third answer. Then with same efficiency calculate the flow rate for the turbines. So, flow rate for prototype we say QP is equal to PP divided by rho G HP into efficiency. So, PP is equal to 30,000 kilowatt, HP 61.8 meter, and efficiency is 90%. So, this will give you QP is equal to 55 meter cube per seconds. So, prototype flow rate is 55 meter per second. And the last problem is about the comparison of turbines. So, what we have is that in a hydropower systems, water is available at a flow rate of 200 meter cube per second and head 20 meters. So, we can say what is the power available with water. So, we can say, or it is water power. So, that is P is equal to rho G H Q into efficiency multiplied by 10 to the power minus 3, which is kilowatt. So, putting this number we can say P is equal to 1000 into 9.81 into H is 20 meter into efficiency is 85% into 10 to the power minus 3 into flow rate. So, P stands as 33354 kilowatt. So, this is the power available for water or water power. Now, we have choice for the turbines, and these turbines should run at RPM of 50. So, first case 1, we say it is a Francis. So, we have speed as 150 rpm and its maximum specific speed is 460, and that is nothing but n square root of p divided by s to the power 5 by 4. Okay. So, here h is equal to 20 meter and n is equal to 150 rpm. So, this will give you power for Francis turbine will be 16823. So, a single Francis turbine will give you 16823 kilowatt power. So, number of turbines n will be 33354 divided by 16823. So, it is approximately 2. So, we need to have 2 number of Francis turbines. For same situation, if you look for Kaplan, that with same rpm, but its specific speed as 350 and that remains expression becomes same as s to the power 5 by 4 n square root of p h to the power 5 by 4 and here h stands at 20 meter. So, this will give you power developed by one particular one Kaplan turbine would be 9739.3 kilowatt. So, from these specific speed expressions we can find out power developed by one Kaplan turbine will be 9739 kilowatt, and number of Kaplan turbines can be calculated as 33354 divided by 0.54 divided by 9739.3. So, this is approximately 4. So, to produce water power of 33.354 megawatt, if we use Francis turbines, we require 2 Francis turbines. If you use Kaplan turbines, we need to have 4 number of Kaplan turbines. So, this makes an initial judgment in a hydropower stations, how many, what is the requirement of turbines based on the power available from the water. So, with this I complete this hydropower module or hydropower segment. Thank you for your attention.